Hi guys, and welcome to today's video on exponential equations. This is a continuation of the wonderful video series that we've been dealing with in our methods 3 and 4. Now if you're watching this outside of Australia and going, what on earth is methods 3 and 4? Don't worry about it. Maths is a universal language, and whether or not it's related to a course here in Australia, the United Kingdom, India, America, it doesn't really matter. All of this is relevant. So thank you very much for sticking with me and watching. Now if you haven't already done so, do me that honour please of seeing that red arrow over there asking you to subscribe. I promise you I'm making no money from these videos whatsoever, and I'm really not trying to be famous. Just want to know that people are actually watching them. Yeah, there are so many videos out there with people watching food. It would be nice to know that occasionally a maths video is being watched. So and if you could tell your friends, that would be also great. Now exponential equations is what we're dealing with today. In year 10 and 11, we've already dealt with the idea of a number of rules. And funnily enough, I've just recorded a video here for year 10, which talks about the zero power and adding indices together and subtracting them. And very much a case, these rules here became critically important, or they're used all over the time. And sadly, many people, because it's algebra, make fundamental mistakes. And these rules just mean something like, for example, if I had x squared times x cubed, because that's the times between and they're the same, then that becomes x to the power of 5. Why? Because you add the indices together. If I had x to the power of 3 divided by x to the power of 2, what do? Well, yes, we should shortcut. Remember that we subtract our powers. The ones that become really funky and important are what I call powers of powers. And when we raise a power to a power, that basically means that's the same as either a squared times a squared times a squared, which is a to the power of 6, or we can use a shortcut that says when you raise a power to a power, you multiply those powers. And that's true even if we have things inside my brackets. You raise everything inside those brackets to powers. So a to the power of 4 because it's 2 times 2, and that would become b to the power of 6. And we need to make sure that even when we have numbers inside of there, that they get raised to the power as well. So if I had 2ab squared, for example, to the power of 3, we'd have to make sure that we raise the 2 to the power of 3 as well. So 2 times 2 times 2 would give me 8, and that would be a to the power of 3 and b to the power of 6. That type of question there is one that trips people up all the time. Here is my 0th power. That's the one I've literally just done for my year 10s. And there are the other two fractional ones as well, which are really just a play on these here. Now, exponential equations are freaking awesome and used in maths all of the time. And you're going to say, really? And I'm going to say, oh, yes. Now, there are two ways of solving them. One, if you're really, really lucky, just by looking at them, you'll know the solutions. Others are using exponentials and logs, which we come to in a later section. And exponentials and logs are freaking awesome. Now, you're going to say to me, but hold on a moment, you've already used the word exponential here. And yes, I have. Exponential equations are those which grow in an exponential way. This question here is a prime example. So we have 5 to the power of x equals 3125. Now, probably slightly outside the idea of this, but if I was to draw this graph of 5 to the power of x, let's imagine here is my y value, here is my x value, and we have 0, 1, 2, 3, and so we go on. Now, with an x value of 0, what will 5 to the power of 0 be? 1. Absolutely. Anything to the power of 0 is in fact 1. What about 5 to the power of 1? Yep, it's going to be 5. What about 5 to the power of 2? 25. So that's going to be up here somewhere. And what you notice is this graph does this, and it grows pretty quickly up. Is there any negative value? I mean, obviously here I seem to have started at the value of 0. Well, actually, as it turns out, there is. And that line continues down and gets closer and closer and closer to the x-axis, but never actually touches. And again, slightly beyond the course here. So when we solve exponentials, we're looking for the base number here to be the same. So what we're really saying is 5 to the power of x is equal to, well, 3125 is 5 to what power? Well, I can't work that out. So we've got 5. 5 times 5 is 25. 125. 125 times 5, 625. Times that by 5. Well, back to pencil and paper ways. 5 5s are 25, 2 5s are 10, add 2 is 12, 6 5s are 30, 3 1 2 5. And ladies and gentlemen, using pencil and paper, I know that 5 to the power of 1 2 3 4 5 is 3125. So I can write that as 5 to the power of 5 just by using basic arithmetic. And now we just compare. With these numbers here the same? then I now know that those powers must be the same. So x becomes equal to 5. 5 to the power of 5 is 3125. And we use the same example all the way through. Here we've got 3 to the power of x minus 1 equals 243. Now ideally, I'm saying to myself, well, I've got 3 to the power of x minus 1 is equal to 3 to what power? 243 can be changed into 3 to what power? Well, again, I've got a 3. 3 3s are 9. 3 9s are 27. 3 27s are, try that one again, 81. 3 lots of 81 happens to be, 243. So 243 can be re-expressed as 3 to the power of 1, 2, 3, 4, 5. And by luck again, it is 5. So I can now rub out that question mark and make that to the power of 5. Again, what I'm trying to do is get all of my terms, and in this case there's one on the left and one on the right, to all be to the base of 3, to have that capital 3, that big 3, so I can find the power. Now, if this here is the same on both sides of that equal sign, then so must my powers. And I can now say that x minus 1 must equal 5, and in which case, therefore, x is equal to 6. See what I'm doing? Now this is a very powerful trick and it uses in all sorts of maths. We can even get more complicated. We can have 5 to the power of 2x minus 4 is equal to 25 to the power of minus x plus 2. Now I'm not bothered about the powers at this moment in time. I'm trying to make these values here the same. And it's easier to turn it's easier to turn 25 into a power of 5. Well, I know that 25 is the same as 5 squared. So I'm now going to replace that 25 with the 5 squared. This stays the same. 5 to the power of 2x minus 4 is equals to 5 squared. Now I'm going to put that in brackets because that is, once again, all to the power. And do you see what the next rule is? Well, index laws say that when you have a power of a power, what do? You multiply them together. So 5 to the power of 2x minus 4 is equal to 5 to the power, well, this 2 is now going to multiply by everything there. So minus 2x plus 4. Are we now in a situation where we can compare and equate powers? Well, of course we are, because if the 5 and the 5 are the same, then these powers must be identical as well. So what I have, 2x minus 4 is equal to minus 2x plus 4. Right, I'm going to add 2x to both sides. I get 4x minus 4 is equal to 4. Add 4 to both sides gives me, continuing over here, 4x is equal to 8. And so x is equal to 2. All I'm doing is comparing and changing. Now, the following types of questions appear on exams all the time, and they are literally favourites of maths teachers. Why? Because they compare or they combine a lot of subjects together. Basically, in this particular example, as I'm about to do, they combine quadratics and powers. You're going to say, huh? Now, the trick is to noticing the pattern. Notice how the question is written. If you look at the question and you've preconditioned your brain to look for certain, indicators, then your brain will just go, yes, I know this is a quadratic, bang, 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 and it's pretty formulaic. All right, so here is one example. Solve for x the equation 9 to the power of x equals 12 times 3 to the power x. What? Now, what I'm going to say to you is this section here, this bit here, is actually the important stuff, because when I see 12 times 3 to the power of x, my brain goes, it's a quadratic. Now, to be able to solve a quadratic, I need to make it equal to 0. So what I'm going to do is I'm going to say, right, that becomes 9 to the power of x minus 12 times 3 to the power of x plus 27 equals 0. And you're going to say, well, that hasn't made it any clearer, but it will. The next hint for these questions is this 3 to the power of x. Now, what it's saying to you is, if you see any other powers, try and change them so they have a base number of 3. If it was 4 to the power of x, try and change it to a base of 4. And it just so happens, the other power I have is 9 to the power of x, which I know that 9 is the same as 3 squared, all to the power of x. And do you see it again? A power of a power. Oh yes, I should cocoa. 3 to the power of 2x. Now, actually, I'm not going to write it like that. I'm going to flip these things around. 3 to the power of x all squared. Now, bearing in mind a moment ago, I said a quadratic. And for it to be a quadratic, we need to have a squared term, an ordinary term, and a number. So this particular instance, because I know it's a quadratic, I'm going to just, rather than multiply those powers together, I'm going to flip them. Watch what happens. Oh, it's very exciting. Watch with mother, and I'm not mother. That's a whole new weird thing. So 3 to the power of x all squared minus 12 times 3 to the power of x plus 27 is equal to 0. Any the wiser? Well, hopefully now you're going to look at that and say, well, hold on, I've got a squared term, I've got an ordinary term and a number. And you're going to say, well, what? And I'm going to say, look, what I'm now going to do is say, let a equals 3 to the power of x. 3 to the power of x looks really confusing. So I'm going to take it out. And I'm going to say, right, everywhere I see a 3 to the power of x, I'm going to put a in. And that's a fudge, it's a trick, because later on we're going to put the 3 to the power of x back in. But 3 to the power of x, there we go, that becomes a squared minus 12 times a. Well, I don't need to write 12 times anymore, I can just write 12a plus 27 is equal to 0. And lo and behold, do you see a quadratic? Well, I should Coco, so I'm going to t-method it. What do I have? 27, so that's 1 and 27, 3 and 9. Okay, well 3 and 9 now to give 12, but I want minus 12, so it's going to be minus 3 and minus 9. And do they add together to give minus 12? They certainly do. So then that becomes a squared minus 3a minus 9a plus 27 equals 0. Factorize by grouping, so take out a, gives me a minus 3. Take out the 9 there, gives me a minus 3 equals 0. And so I end up with a minus 3, a minus 9 equals 0. Now I've run out of room, so I'm going to move over to the other side of the screen. So therefore, we know that a minus 3 equals 0, or a minus 9 equals 0. And you're going to say, well, that doesn't look like an a for a start. No, I agree with you completely. So a is equal to 3, or a is equal to 9. And you're going to say, but how does that solve my question? Well, it hasn't. That's not the end. We just wanted to make our quadratic look nicer. Now, some people out there are watching this and going, well, I could have just done that in my head. Absolutely. Knock yourself out. Much respect. What I'm now going to say is I'm going to switch the question back and say, well, I don't want a anymore. I want to say 3 to the power of x is equal to 3, or 3 to the power of x is equal to 9. And so what power of 3 gives me 3? 1. And what power of 3 gives me 9? 2. And there we go. Solving these quadratic things. Now, I promise you, these are on exams all the time. They are a fabulous question, right? And again, we've got another example here, slightly different. But I see that this 6 times 3 to the x. Now, there are lots of people who would write that as minus 18 to the x, and that really worries me. You can't do that. Sadly, it's not correct algebra. But what I'm going to do is follow my rules again, flip them around. And I'm going to make 3 to the power of 2x plus 6 times 3 to the x minus 27 equals 0. Now, seeing that 27 again, don't get fooled into thinking it's the same thing, right? Because it's slightly different. I've got 6. Hold on a moment. They've got 3 to the power of x here, but they've got 3 to the power of 2x. Well, again, go back to this previous example. Remember when I told you that we could write this as 3 to the power of 2x, but we didn't want to? Well, the point of it is now you're going to split it up. We know that powers of powers can be written different ways. So I can write this 3 to the power of x squared plus 6 times 3 to the power of x minus 27 equals 0. Once again, let's let a equals 3 to the power of x, and it's not always 3 to the power of x. So we get a squared plus 6a minus 27 equals 0. T method minus 27, so I want 1 and 27, I want 3 and 9. Now, as it turns out in this situation, 3 and 9 is correct because I want minus 3 and plus 9 to give me that plus 6. So a squared minus 3a plus 9a minus 27 equals 0. Move it up a bit so I've got some room. Factorize by grouping a minus 3. Take 9 out. A minus 3 is equal to 0. Oh, it's so exciting. A plus 9 and a minus 3 is equal to 0. And so, therefore, we know that a plus 9 equals 0, so a is equal to minus 9. Or a minus 3 equals 0, so a is equal to 3. Well, that's not the end of my question, so I put my a back in, which remember decided was 3 to the power of x is equal to minus 9. And 3 to the power of x is equal to 3. Well, this one's nice and easy. X is equal to 1. But look at this one here. 3 to the power of x is minus 9. Is there any floating number I can make 3 to give that minus 9? And as it turns out, no. And it's actually perfectly valid to put a cross through that and say, no valid solution. Not all quadratics will end up with 2 solutions, particularly with exponentials. And so my only answer here is x equals 1. Now, please don't just leave 3 to the power of x equals minus 9 and expect your examiner or your teacher to just go, oh yeah, they obviously know what they're talking about. The thing about maths is you have to look at it and go, all right, that's not possible, cross it through, job done. All right, ladies and gentlemen, this is fabulous. Ready for a 45-second recap? I am. We started today with exponential equations, where we recapped those basic laws you were shown a long time ago with all those floaty x and n's, and we did some examples to show why. We also looked at how to do powers of powers and multiply them out. We looked at examples of exponential equations. We looked at the idea that initially they link to some sort of graph, and then we were looking at examples with 1, 2, 3, where ultimately you were trying to make that base number the same and equate coefficients. We moved on to this fabulous example of solving for x, basically quadratic equations that are in disguise. And using 2 examples, we looked at the fact that there were solutions and no possible solutions, and breathe. Ladies and gentlemen, as ever, it is fabulous having you watch these videos, and thank you so much for dropping by. If you can you get out there and tell your friends about the channel? Tell them on YouTube or Facebook or Instagram or any of those other wonderful things out there that I'm way too old to understand. And if you can and haven't already, there is a subscribe button for you to subscribe to. Greatly appreciated. And if not, I'm sure there's a video loading over there somewhere of the similar caliber for you to watch. Again, thank you so much for taking time to watch. It's been good. MaffsGuru out.